What if heat generated by splice losses could actually correct the splice? That's not a thought experiment, that's what we came up with. We are Preston, Chang and Lorraine Chavula, and this is our self-healing fiber optic splice system. Here's the scale of what we're talking about. Over 400 transatlantic cables, more than $50 million and weeks of downtime to fix a single break. And every repair leaves the joint weaker than before. Subsea cables carry 99% of all international internet traffic. When they fail, the repaired joint becomes a permanent weak point in the network. This is not a niche problem but a global vulnerability. Just to further show how significant this is, BBC Future covered this exact problem last year. There is 1.4 million kilometers of cable sitting on the ocean floor. Each cable is just about 2 centimeters wide, and when one breaks, it takes 10 to 12 days for a repair ship to arrive at the sea. In 2022, a volcanic eruption near Tonga snapped their only subsea cable. The entire country lost internet for 5 weeks. 5 weeks offline just because of one bad joint. That's what's at stake. So why does this keep happening? Even when a repair looks successful, the physics works against it. Getting two fibers perfectly aligned at a micron scale is incredibly hard. Even a tiny offset causes real power loss. That lost light doesn't just disappear, but it turns into heat. And that heat expands the materials around it, which shifts the alignment even further. When the cables get damaged, the fiber inside breaks and it never breaks cleanly. You might get a gap, a physical separation between the two fibers, or a tilt, which one fiber is angled relative to the other, or even an offset where the two fibers are parallel but shifted vertically. Any of these destroys the coupling efficiency. And the result is a lost signal, data that never arrives with loss that has nowhere to go. That lost energy just doesn't disappear. It's converted to heat, right at the splice, a concentrated hotspot forming exactly where the fibers misalign. This is the problem, but it's also, as you see, the solution. Here's our geometry. Two fibers, each 100 micrometers long. The core is 9 micrometers wide. That's germanium doped silica. Around it sits a pure silica cladding with a 30 micrometer diameter. The slight difference in refractive index between the two is what keeps the light bouncing inside. This is total internal reflection. We modeled all the three failure nodes I explained above: a gap, tilt, and offset. Each one degrades coupling differently, and we simulated the transmission loss curves for all three. In an ideal world, the light transfers cleanly, perfectly coupled, no loss, no heat. And this is what we are aiming to restore. Instead, this is what happens. Notice how most of the light spills out underneath the second fiber. It never transmits at all.
So, what are the effects of the tilting, gaps, and offsets? Here's a plot that tells us how the signal degrades as the gap widens. There's a lot of transmission loss over here, with a sharp turn, almost like an exponential. It's similar for tilt. As you significantly increase the tilt, then the signal gets lost very quickly. The same effect is for offset, but note that the distance is much smaller than in the gap. So we realize that all of these parameters have a similar effect on the signal, but by far the most sensitive one is offset. In fact, the industry standard involves fusion splicing the fibers together. This removes the gap. And since you could easily angle a long piece of wire, tilt turns out to not make a huge difference either. Offset is the real killer here, responsible for most losses in transmission, which is why our solution focuses mainly on that.
So here's our idea. The problem, which is wasted light turning into heat, is the solution. First, light enters the fiber on the left, and any spilled light travels through the cladding of the next fiber. Next, a circular mirror positioned just 30 micrometers into the second fiber catches the spilled light and reflects it back towards the first fiber. Then that reflected light warms a heat-responsive polymer jacket at a radius of 15 micrometers. Lastly, the jacket expands, but it's encased in a rigid outer cylinder, so expansion has only one place to go. It pushes the first fiber closer to the second, improving coupling, reducing loss. The system corrects itself using the energy it was already wasting. This is just a summary of everything I explained above.
Here are the equations we use. For optics, we have the Hamiltonian wave equation as shown. For the thermal effects of the rays, we have the heat equation, and for the thermal expansion, we have basic solid mechanic equations and thermal strain equation. In case what we just explained was a bit confusing, here's a little visual for you to see what the light rays do. As with before, the light rays are mainly coming through the bottom, but this time they reflect off the mirror and then get absorbed by the polymer jacket and the absorbent conducting surface. This produces the following steady-state heat map, derived from the positioning of the rays in the previous slide with some power assumptions, seen above. Note that a lot of the rays land on the conductive surface. If this wasn't there, they'd pass through the glass again and wouldn't be absorbed. This affects the stress on the system, resulting in a certain strain, represented by this arrow diagram. Don't worry about the particulars of it though, since it's really the displacements that we're after. There is the steady-state displacement for fiber A, which has light reflected on it. You can see the polymer expanding. See that around the bit that was heated, below this little circle, the bottom bit of the polymer has negative displacement, meaning that it moves lower, and the bit of the polymer on the top has positive displacement, so it moves higher. The actual fiber has a slightly positive displacement, averaging around 0.68 microns. We see a similar effect for fiber B, but on a much smaller scale, since the silica glass has a lower coefficient of thermal expansion than the polyethylene. Here's the average displacement of the fiber. It's 0.28 microns, resulting in a net correction of about 0.4 microns. This doesn't seem like much. Remember, we're dealing with scales around the 1 micron. So yes, this is significant. An offset of a whole 4 microns will only see a correction of about 0.4, but the current technology and skilled workers won't make that much of a mistake. Instead, we'll be off by only around 0 to 1 micron, and you can see that correction almost matches the offsets. And that brings us to some tangible evidence. It's clear that this jacket outperforms a cable without the correction, especially at lower initial offsets. Not only does this mean more information is passed on, but it also means lower attenuation, which can help us save on relays further along. It'll be as if there was no offset or damage, and then the only difference to the installer is just slipping on the jackets when they finish splicing the fibers. There's less of a worry about accuracy. Here's a little summary of the entire process if you want to pause and review. Of course, all models have their limitations. This only looks at the innermost workings of the fiber optics and doesn't account for the larger outsides. Also, the silica glass cladding is smaller than in real life, though this doesn't matter since we capture the essential physics. The jacket only works unidirectionally. It by design cannot support healing if light moves the other way. This is fine though, since the cable has close to 100 fibers, meaning that directions can be easily assigned to each. We did not model environmental conditions like seawater, though the cables are self-contained pretty well. We also used geometric optics to model in COMSOL, not representing light as full electromagnetic waves, and we assume that the materials have linear responses. However, these are smaller approximations and shouldn't make that much of a difference to the model. To round this off, this proof of concept shows that we can use the laws of physics to naturally fix errors. With further funding, we can develop this idea further and hopefully see these jackets implemented in the future. Thank you.